Welcome to the NPTEL Symmetry and Group Theory interactive session. This is our first interactive session, and here we will be discussing about parity operators, and we will be solving some basic problems on parity operator. So, with the help of these interactive sessions, we will be taking up some model questions that will help you in solving assignment problems also, or you can also ask your doubt related to class or any doubt you have in these sessions. Let's begin with our first session. What is a parity operator? So the parity operator is defined on position space wave functions by reflection about x equal to 0. So when you apply this parity operator on a function, you replace the x with the minus x, and you see if the this parity operator will give an eigenvalue of +1 or -1. If it is +1, then it is symmetric. The wave function is symmetric with respect to parity operator, and if it is minus psi x, then it is anti-symmetric with the parity operator. So the eigenvalues will be 1 or -1. Uh, and in three dimension, it is defined as p psi r is equal to psi of minus r, where it is we are showing it in the three coordinates x, y, z, or other polar coordinates, etc. We can also take up. So, uh, so it is very well understood that even functions are symmetric with parity operator, because when we see that if a function is giving us fx is equal to f minus x, when we are substituting x with minus x, we are getting fx is equal to f of minus x. Then it implies that the function is symmetric with parity. So this is the equation we follow. Just a minute. So this is the equation we follow for parity operator. So even functions are always symmetric with the parity operator. Let's take up some examples. So this is the example we are taking, fx is equal to x square plus 1. So here what I have done is, we have taken fx is equal to x square plus 1. So if you replace, that is substitute this x with minus x, then the equation will become like this, and minus square of minus x is x square plus 1. So we are getting the same function, that is fx, which means that fx is equal to f of minus x. That is, this is an even function, and it is symmetric with the parity operator. Similarly, if we take a cosine function, so if we replace this x with cos of minus x, we will get cos x again, that is fx is equal to f of minus x. So we are well aware that uh, if we plot this cos x function, we get this kind of plot for cos x. This is 0, pi by 2 minus pi by 2. So this is showing that this wave function is symmetric. But when we see functions like sin x, we got this kind of graph, that is, which shows that sin x function is an odd function because sin pi by 2 is giving us 1 and sin minus pi by 2 is equal to minus 1. So this helps us in defining which function is odd or even. So an even function is always symmetric with parity operator and odd function is asymmetric with the parity operator. So let us take another example here. So please note this is the equation which follows for the parity operator with respect to an odd function. Okay. So if we see here, if we take this example, x of x square minus 1, and we substitute this with minus x, what will we get? Minus x square of minus x minus 1, which is minus x into x square minus 1. So what we are getting is g of minus x is equal to minus gx. Therefore, this function is odd. Okay. So these even and odd functions. So based on these symmetries, these symmetries in operators and wave functions help us in finding out some solving some problems in spectroscopy also. For example, in spectroscopy, to find out the transition dipole moment integral, which is the dipole moment induced in a molecule during a transition. When a transition from a ground state to some excited state is being induced, then we using this integral we predict whether this transition to the excited state is possible or likely, like it will happen or not, is it possible or not. So this whether this transition dipole moment integral, this I is transition dipole moment integral. So it has a corollary for it, like the conditions what which has to be followed for a transition dipole moment integral to be equal to 0. And what does it say? It says that this operator, so please consider these parity operator and these have this sign on it. So if this operator commutes with parity operator, then first condition is we have to check whether the operator O commutes with parity operator. If this condition is fulfilled, then we have to check whether this psi and psi j integral, either of them should be odd. Like one of them should be even and other should be odd. Like they shouldn't be, both of them shouldn't be even and both of them should not be odd. So they have to be either odd, one of them should be even and one of them should be odd. So this is the condition, psi I psi j is even and other one is odd. If these conditions are fulfilled, then we will get transition dipole moment integral equal to 0, and if not, then I is not equal to 0. That the transition from this excited from a particular ground state to that excited state is not possible there. Okay, so for now we will check how we will find out how to check an operator commutes with parity operator or not. So firstly, let me tell you what is this commutator thing. Commutative property. So this says if we have two operators A and B, A and B, then representation of this commutator is like this. We represent these two operators which commutes like this, where we are checking the commutative property. So how it follows? AB minus BA will equal to 0. That is BA. So if this condition is fulfilled, then operators A and B are said to be okay. So now we have to check whether a particular operator, we will take some of the operators, like firstly we will be taking this position operator and we will check whether this position operator commutes with the parity operator or not. So the position operator is this is the position operator. If it applies on a certain wave function fx, show you presented as, so if this operator x operates on a function fx, wave function, then we will get x of fx, where x is the eigenvalue. Okay, so this is the condition. This is how the position operator operates. So now we will check whether this position operator is commutative with the parity operator. So what should happen? Firstly, we will write the condition for the commutative. It should be 0. Okay, if they commutes. So let us take a wave function fx is equal to x cube. And we will operate these operators, position operator x and this parity operator p, on this wave function fx is equal to x cube. So this x of p operating this firstly this parity operator will operate on the fx. So x p cube. So for this parity operator we will substitute x with minus x and take q out of it. So what will we get? X of minus x cube, that is minus x operator will now operate on this x cube. Okay, so what will we get? We will get minus x into x cube, that is equal to minus x4, because this is what we get. So here fx is equal to x cube, so we will get x into x cube. And minus we got from above when we operated the parity operator. Okay, so this is we got for p is equal to minus x4. Now after exchanging the position of these operators, this is what we get when we first operate the position operator on the x cube, and now parity operator will operate. We will replace x with minus x and take a power of it. So here what we get is x4. So p of, so if you see, are these two things equal? No, they are not equal. So therefore we can say that position operator doesn't commute with parity operator. I hope it is clear. So let's take another example. Now we will check whether momentum operator commutes with parity operator or not. So I'm representing this momentum operator as small p, like this. Okay. So when this momentum operator operates on a wave function psi x, we will get minus iota h direct del by del x of psi of x as the where as a result where psi x is the wave function and this is the eigen value. Okay, so now we will check whether this momentum operator commutes with parity operator or not. That is, when we exchange the positions of these two operators, whether it is equal to 0 or not equal to 0. Okay, so here we will again take this if psi x, or we can say fx, this wave function we are taking is x cube again here. Okay, so now let's operate this. Firstly we will find out so what does parity operator do. It will substitute x with minus x. When we substitute this x with minus x, what will we get? Minus operator, momentum operator p into x cube. Now this momentum operator will operate on this x cube, which is minus iota h direct del by del x cube. So what we will get? We will get 3x square on differentiation. That is 3 iota h direct x square. So now let us check whether this is giving us the same value, that is 3 iota h direct x square, or something else. Parity operator, momentum operator is minus iota h direct del by del x operating on fx, which is I'm taking this minus iota h direct outside, so del by del x of x cube. It will give 3x square. So now taking this 3 out, minus 3 iota h direct, this parity operator will now operate on x square. So what will we get? We will have to substitute x with minus x, then we will get, and square of minus x is x square, so we get minus 3 iota h direct x square. So these are the two different results we are getting. That is, we can see p of p fx is not equal to, which means momentum operator doesn't commute with parity operator. Okay, I hope this is clear to you. So the position and momentum operator doesn't commute with parity operator. We can also check whether kinetic energy operator commutes with parity operator or not. So let us check. So here we got, as you can see, we got a minus sign, that is P. This Here this P, uh, this momentum operator. Here we are getting opposite signs for these things. So we can say that position and momentum operator are anti-symmetric with the parity operator because we are getting a minus sign out of it. Okay, because f of x is equal to minus f of x after operating these operators. So now let us check whether kinetic energy operator commutes with parity operator or not. So what is kinetic energy operator? It is equal to minus s direct square by 2m del square by del x square. So I'm taking these operators in only one coordinate, x coordinate only. You can also take it in the xyz coordinate, like uh, mm, three coordinate system also. Okay. For simplicity, for explaining how to solve these problems, I am taking it in one coordinate only. So let us take fx is equal to uh, e raised to minus x. Okay, so we will check whether this kinetic energy operator commutes with parity operator. We got e raised to x. Now we will operate so while double differentiating this ex, what will we get? We will get e raised to x only. Minus s direct square 2m del square by del x square of e raised to minus x. Taking this minus x direct square 2m out, we will get minus del by x of e minus x and p and again differentiating this e minus x, we will get e raised to minus x. Now we will operate this parity operator. What will we get? We will get ex. So we can see that both of these are same. So what we can say that kinetic energy operator commutes with parity operator. So now let us take another example where we will be taking the ground state of simple harmonic oscillator. We'll be taking the wave function for the ground state of simple harmonic oscillator, and we will check whether for this function this kinetic energy operator is commutating with parity operator. So from here you will get a conclusion which I'll be telling you after solving this problem. Ground state of simple harmonic oscillator, which is psi of x is equal to a e raised to minus beta square x square by 2. So here we will check whether the kinetic energy operator commutes with parity operator or not. So kinetic energy operator is del square by del x square, that is minus h direct square 2m del square by del x square. So firstly let us find out when the parity operator first operates on this wave function we have taken. So here we will replace x with minus x, and what will we get? We will get square by 2. So this function is symmetric with respect to parity. So we will get a outside and this kinetic energy operator will now operate on this, which is minus h direct square by 2m del square by mid by del square by del x square e raised to minus beta square x square by 2. So I'm taking this out. So what will we get? We will get minus 2 beta square x by 2 into e raised to minus beta square x square by 2. I'm taking this out, minus a beta square h direct square by 2m, and differentiating it again, this x into e raised to minus beta square x square by 2. What will we get is 1stly we will differentiate it, keeping it constant. We will get e raised to minus beta square x square by 2. Then keeping x constant, we will differentiate this e raised to minus beta square x square by 2, and we will again get x into x e raised to minus beta square x square by 2. So finally what we'll get is one plus x square minus e raised to minus beta square x square by 2. This is what we get for e raised to p operating on psi x. Now interchanging the positions, and again applying on this psi x, what will we get? Our function is a e raised to minus beta square x square by 2. So here I'm taking this out. What will we get? Uh, we will get del by del x of e raised to minus beta square x square by 2. So again differentiating it, what will we get? I must have done a sign mistake, I think. Let me check it again. Okay, I've done a mistake. Let me check. Let me do it again. So here we will get beta square. Taking this minus sign here, so it will become plus. And here we will have beta square also. Yeah, beta square I have already taken out. Okay, then again here also I will get minus beta square. So we will have 1 minus beta square x square, the answer here. Okay, so here also if we will become plus x square e raised to x square by 2. This is what we will get. So a s direct square by 2m, and we operate this parity operator on this now. So we will get this e raised to minus beta square x square by 2 as it is, because square of minus x will become x square. Similarly here also this is what we will get. So the conclusion is 1 minus beta square x square a h direct square by 2m into e raised to minus beta square x square by 2 is what we will get as an answer here. So we can see we are getting same results from both of these, that is e raised to e operator commutating with parity operator, that is kinetic energy operator. With parity operator. So whatever function we will be taking, we will have to check for the first condition that our operator, is it position operator, momentum operator, kinetic energy operator, or it might be Hamiltonian operator also. You will have to check and whether this operator is commutating with this parity operator or not. So now from these examples we are clear that position and momentum operator doesn't commute with parity operator, and kinetic energy commutes with this parity operator. So next is we will be taking one example to see with whether given function is symmetric or anti-symmetric with an operator. Sorry, with parity operator. So to check for whether a function is symmetric or anti-symmetric, we will replace this x with minus x in the function. As we know that sine function is an odd function and cosine function is a is an even function. So what we will get, minus sine 2x plus cos 2x. So here when we take this minus sign out, what will we get? This f of minus x is equal to this. So here we can see that f of x is not equal to f of minus x. It is neither symmetric nor anti-symmetric with respect to parity. We are getting different result here. So the given function with respect to parity. So let us take more examples here. Uh, Let us take a function fx is equal to x square plus sin x plus 1. We will check whether the given function is symmetric or anti-symmetric with parity. So similar to previous examples, we will substitute with minus x. For this we will get x square, but for sine of minus x we will get minus sine x. So f of x is not equal to f of minus x. The given function is neither symmetric nor antisymmetric with parity. So now let us check a few examples for where we will be taking some functions and different operators, and we will find out whether the given transition dipole moment integral will be 0 or not. So this is momentum operator. This is what we are taking. Okay. So the first condition for the corollary for this transition dipole moment integral to be equal to 0 is this momentum operator P must commute with parity operator. But in our earlier examples, we have already found out that momentum operator doesn't commute with parity operator. As we know, parity operator. Therefore, I is not equal to 0. So the first condition is not even satisfied, then there is no benefit of moving to second condition. We have to make sure firstly our first condition is satisfied, and then we will move on to second condition to find out whether this psi I, that is x cube here, and psi j, that is cos beta x, is which one of them is even, whether both of them are odd, or whether both of them are even. So based on that we will go on second condition. When our first condition is not fulfilled, then from that only we can conclude that transition dipole moment integral I is not equal to 0. Okay. Mm. So here let us take another operator for this same example. Hamiltonian operator. So what is Hamiltonian operator? Hamiltonian operator is sum of kinetic energy operator plus potential energy operator, which is minus h direct square by 2m del square by del x square plus v of x. So this Hamiltonian operator always mm, commutes with parity operator. So this you can find out by solving by applying this operator, checking it with by changing the exchanging the positions with the parity operator. Just check it out whether H P is equal to that is equal to 0 or not. So I'm saying you, I'm informing you that confirming this that Hamiltonian operator always commutes with parity operator, but you also try it once yourself. Okay. So now let us check here. So our first condition is satisfied. is satisfied here. Yeah. Okay. Now the second condition is psi I or psi j, either psi I is even and psi j is odd, or psi j is even and psi I is odd. Okay, so here let us check this x cube. X cube is odd function, and this cos beta x we have already discussed is an even function. So here our second condition is also fulfilled. Therefore here integral of transition dipole, this transition dipole moment integral I is equal to 0. Okay, now let us take another example for this. E raised to minus x cube kinetic energy operator sine square beta x. So as we know, kinetic energy operator E commutes with parity therefore our first condition is fulfilled. First condition of corollary is fulfilled. Now let us check this e raised to minus x cube is an odd function or an even function. For this, we will apply parity operator on it. What will we get? E raised to cube. We will get e raised to x cube. So this is an psi I is an odd function. And this sine square beta x, if we see its graph, we will see this kind of graph. Okay, if we plot a graph for it, we will get a symmetric plot. This one is not properly shown symmetric. Let me try to draw it again. So sine square x and cos square x are even functions. Square of sine x and cos x both are even functions. So sine square beta x is an even function, that is symmetric function. So here a second condition that either of psi I and psi j should be even, sorry, uh, uh, even function, and another should be odd function. So that is also satisfied here, right? Therefore, transition dipole moment integral is equal to 0. So these were the problems I wanted to solve for the parity operator. So if you have any doubts, you can post it in the discussion forum and I'll try to help you there, or we can discuss in the next session also. So when I took this session on 5th of Feb, uh, due to some network issues or some recording issues, I couldn't get proper recording, and the class didn't go properly because of some issues. So and but there we were discussing some molecules where we were finding some symmetry operators, like some symmetry elements present in in a certain molecule. So basically, we were discussing proper axis of rotation and plane of symmetries in some molecules, uh, and we took some basic examples there. So, but here in this session, when I am repeating it, I have taken parity operators mainly, uh, problems on parity operator. In the second session, I have tried to find out all the symmetry elements, that is proper axis of rotation, improper axis of rotation, plane of symmetries, inversion center in some molecules. So you can get a guide of that of in that session also. Here, let us take a few examples, and then we will move on to some basics of these symmetry elements and operations. We will take some examples. Okay. So let us take I is equal to x square plus 1 Hamiltonian operator e raised to minus beta square x square by 2. So Hamiltonian operator, we know, commutates with parity operator. Condition 1 satisfied. Condition 2, x square plus 1 is an even function. and e raised to minus beta square x square by 2 is again an even function. Therefore, condition 2 of corollary is not satisfied. So here we will get transition dipole moment integral I is not equal to 0. These are some of the examples. Okay. So let us discuss some molecules where we will find out proper axis of rotation and reflection planes, that is a plane of symmetry. So in the first session, I was asked a doubt on this problem, that cos x d square by dx square e raised to minus ax, and the student was asking whether we have to check whether this operator d square by dx square is commutating with parity operator or not. We have to operate it on e raised to minus ax or cos x. So basically, you have to check this operator commutating with parity operator with respect to any function you can take. So if it satisfies the condition, then it will satisfy with every function. So let me show you it here. So if you check this operator, d square by dx square, and we are taking the function as e raised to ax. Okay, so when operator O operates on this fx, will when this parity operator operates on e raised to ax, we will get e raised to minus ax, and then we will operate this d square by dx square on e raised to minus ax. So what will we get? We will get minus a d by dx e raised to minus ax, and then again a square e raised to minus ax. This is what we will get. And again, if we check this by interchanging the positions, e raised to minus ax, we will get minus a d by dx of e raised to minus ax. We will get minus a e raised to minus ax, that is a p operator of parity operator now operating on e raised to minus ax. We will get a e raised to min is equal to ax. So this is showing that uh, p of fx, that is op is not equal to o. That is this operator o doesn't commute with parity operator. So let us see whether this d square by this operator o commutes with respect to fx is equal respect to cos x. So O P of fx is equal to O parity of cos x. We will get d square by dx square operating on. From this we will get cos x back because it is an even function, cos x. Then d by dx of minus sin x, minus sin I have taken out. Then we will get minus cos x. So O of this is equal to minus cos x. And when we interchange the positions, fx equal to square dx square of cos x will get sin x minus I have taken out. Then again we will get cos x, and when we operate this parity on cos x we will get minus cos x here. So basically what we have to do is we have to apply the operator on psi j in the equation is equal to psi I o psi j. This operator will operate on this psi j, and with respect to this wave function we will have to find out whether the operator commutes with parity operator or not. I have some doubt here. Give me a minute. Give me 5 minutes. Uh, I'll confirm something here. So let us check this kinetic energy operator here. When it is operated on sine square beta x, is it commutative with the parity operator or not? And the problems as solved follows the pattern or not. Okay, so I'm confirming this. P on fx is equal to, we will get sine square beta x square beta x. Basically, what we have to do is we have to check whether an operator is um, commutative with parity operator by operating the given operator on the function on the left side of it. Sorry, like what I can say, on the right side of it. From left to right we move here. So here we will check whether this kinetic energy operator is commutative with parity operator or not. But there are these like position operator, momentum operator, they never commutes with parity operator. Similarly, kinetic energy and Hamiltonian operators commutes with parity operator. So these things we have to check, and then we will have to find out whether the final integral will be equal to zero or not. So please solve these problems and let me know if you have any doubts here. So So in the first lecture we took this example like ammonium NH4 plus, and then we solved this is 1,2 dichloroethene. So let us revise it here. So this is NH4 plus ammonium cation. So here we have a tetrahedral geometry. Okay, this is tetrahedral geometry we will get here, and the representation will be like this. Now we found out the proper axis of rotation here. So when we represent these protons, these second, third, and fourth proton, which are at 120 degree, like not exact 120 degree angle. This molecule has 109 degree 28 minutes angle between it, which is present in tetrahedral molecules. So when we present them in a kind of a triangle and we move them 120 degree with respect to each other, we will get an equivalent configuration there. So we can see that here we have a C3 axis of rotation, C3 proper axis of rotation passing through rotation, passing through this nitrogen and this H1, like first proton, the proton which is labeled as 1. So we have this C3 axis of rotation here. Okay. Now similarly we have here these protons are at equal angles with respect to each other. So with respect to each proton we will get a C3 axis of rotation. So we will have 4 C3 axis of rotation in this molecule, and then we have C2 axis of rotation also present in this molecule, and for it we represented this ammonium cation in a cube to find out the C2 axis of rotations, which was done as follows. So this is how. So at the center of the cube, this nitrogen atom is present. Then on the alternate diagonal positions, we will have our protons. So, so we have C2 axis of rotation here passing through these two opposite faces C2. One C2 axis of rotation is present here and one is coming like this along the, if I represent it as a G, this is Y and this is X axis. So one C2 axis is coming out of the cube, that is towards X axis. So we have three C2 axis of rotation here, and the plane of symmetries. So we will not have a horizontal plane in this molecule, because if we, like, this is the nitrogen atom and this is the protons, and these three protons, like, one is coming towards you, one behind my hand, and two protons are in plane. So you will see there is no plane perpendicular to C3 axis of rotation, which will give an equivalent configuration. So here horizontal plane is not present, sigma h is not present, but we do have vertical plane of symmetries present. So which are like the plane H1 and H1 and H2 will bisect S3 and H4. Similarly, a plane containing atoms S3 and H4 will bisect H1 and H2. Like a plane containing two atoms in like H1 and H2, which are in plane, will bisect the protons which are out of plane S3 and H4. Similarly, a plane uh, passing through this S3 and S4 plane, which are like out of the plane, will bisect H1 and H2. So here we will have three sigma V planes. And we will have three dihedral planes also, which will be cutting 2C2 axis of symmetries. So this is it for our first session, and we will be discussing further in our session 2. If you have any doubts, you can post it in the discussion forum, and you can also ask me in the next session. Thank you.